It was nice out for a couple of minutes. Now it's cloudy again, but yeah.
Probably one I think being cold.
Well, it was 82, I think, where I was, but yeah, it's pretty warm. It's kind of like on the warm end, but it's going to be like it's been cold and just it's going to dump. It'll be hot, you know.
You get used to the cold, and then when it gets hot,
Yeah, that's true. Yeah. All right, so what do I want to do here? That's one thing. Open. Um, all right, so what do we got? Oh, 10, 12. All right, so let's see. So anyway, I wanted to go through some stuff from rheology that didn't get covered by Casey. So so you see in the books the hydrodynamic effect. That's one thing, and then the draining versus non-draining, and you'll see Zim versus Rouse. So basically, those are all like different ways to talk about the same thing. So when we did intrinsic viscosity, we took like the volume of the polymer coil, then the mass of the polymer coil. That would give you this intrinsic viscosity. Like the intrinsic is going to be the opposite of concentration, so it'll be like volume by mass. So the volume is going to be with the fractal dimension, and then the mass. So you can end up with a Mark-Hoyt coefficient from that. In other words, the intrinsic viscosity goes with the mass to some power, and that power has got to do with the fractal dimension. So that's the Zim model. So you have the coil, and it's treating it as if it's a colloidal sphere of diameter. That's a hydrodynamic diameter, right? So basically, that's one way to look at it. Like, in other words, all the solvent that's in the polymer is stuck with this polymer as it moves around. Right. So that's the Zim model. That's a non-draining model. And that's a hydrodynamic effect would be 100%. In other words, the solvent, so hydrodynamic is like kind of water, but basically it means the fluid that's with the polymer, as far as I understand it. It's like the fluid is stuck with the polymer. So it's non-draining. So it's totally like a colloidal sphere. Anyway, so that's the Zim model. The opposite of that is totally draining, which would be it's a worm, right? The chain's a worm and it moves around as a worm. So that's the Rouse model. Okay, and that's also that would be the total draining model. If you want to deal with in between, where some of the solvent sticks in it, like if you have a protein that's folded and it collects some of the solvent, or a polyelectrolyte that's got charges and the solvent stuck to the surface, then you need to have the hydrodynamic parameter to describe between the Zim model and the Rouse model, where are you? Like, in other words, one's going to have a higher viscosity than the other. Like the Rouse should have a lower viscosity because it's got a lower profile as it moves through the fluid. Anyway, so calculating that hydrodynamic parameter is like a nightmare. Like that's a problem that isn't exactly solved, right? Like, so how much solvent actually sticks to the polymer in its motion through a fluid? Becomes like mathematically like a really complicated problem. So the Zim is absolutely a simple problem. It's just a geometry problem. So you just say the geometry, and then like the fractal dimension comes in because that decides the volume of the of the chain versus a mass. So you get this, you can get predictions from the Zim model, like the diffusion coefficient is going to go with this, the mass of the chain to the -1 by df. Then the relaxation time of the chain would be like the time that it takes to diffuse its own diameter. Like say you have that coil ball, and it's going to move like its own diameter. How long does it take to move out of the place where it is to another place? So that's this relaxation time. If you calculate that, you end up with basically also the power of the molecular weight to this fractal dimension thing, right? And then the viscosity we got with a Mark-Hoek. So if it's a Gaussian coil, it's n to the 1/2. If it's a good solvent, it's n to the 0.8. And if it's a rod, it's n to the 2. If it's a solid object, then it's like n to the 0. It doesn't depend on molecular weight. Or the intrinsic doesn't depend on molecular weight, but the viscosity depends on, I don't remember what it is. df would be 3, so it'd be 0, n to the 0. Doesn't depend on mass. So whatever that means. But anyway, so for Gaussian and good solvent, and then rods would be 2 for this power, because it would be like 3 by 2. 3 by 2, I guess it'd be, let's see, 3 by 1 would be 2 minus 1 is 2, right? 3 minus 1 is 2 per rod. So anyway, that's the Zim model. So we've already kind of talked about that. We didn't call it the Zim model. We didn't call it non-draining, right? So the other model is this Rouse model that's like the fully draining model. And that, so the first time you run into it is when you have a oligomer. So this is the viscosity. When I put this, so you can almost read it. So this is the viscosity, this is molecular weight. Actually, this is the relaxation time, which is proportional to viscosity, but this is viscosity over here, log of the viscosity, log molecular weight. This is a power law dependence. Viscosity goes with molecular weight to a power, but the power isn't like 1/2, the power is 1 here, because the viscosity is proportional to molecular weight. So, and then we get to this entanglement, molecular weight, and then all of a sudden it shoots off at 3.4 power, right? So anyway, below that, that's Rouse dynamics, which means that basically when you see like viscosity and molecular weight proportional, it means that chains, the longer the chain, the higher the viscosity. So you're just adding cars onto the train more or less. And that's kind of the Rouse model for this thing, right? So anyway, so that's like this simple view of the Rouse model. The other place you see it is in, let's see, let me go to slide, oops. So slide 30, I think. Nope. All right, so here, so this is an example of that. Of 28, I guess is what I wanted anyway. So if you look at this is a G prime, G double prime. So storage and loss modulus versus frequency. It's set times AT so that at 1 you're at the viscoelastic relaxation point. So AT would be the shift factor for the point where where you start to see deformation of the chain. So before that, the chains can totally relax. So it just acts like a Newtonian fluid at the low end. And then I think I went through before the dependencies of G double prime and G prime for Newtonian fluids follow this power 2 in frequency and power 1. We were talking about the powers and frequency, right? So that basically that's a signature of Newtonian fluid. If you have a polydispersed sample, it doesn't exactly follow that, but for monodispersed, that's good. And this is from Gracely wrote the book on polymer rheology. So this is some kind of monodispersed polybutadiene, right? So anyway, and then you when you start to see that they can relax, and then you get this basically a tailover, the modulus, and then you get into the regime where you have like the entanglements become important. So you're kind of looking at size scales too. So at the low frequency, it's large size scales. It's a Newtonian fluid at long time. So low frequency is long time, so it can relax like a fluid. And then you get to a higher time, and the time you reach the tau for the relaxation, then the entanglements come into effect. So before that, entanglements don't matter because they can just relax the entanglements, and it's just a fluid. Then you reach that, and then you get a plateau. It becomes like a rubber. And it's got a constant modulus. And the entanglements act like crosslinks. So you're at a time where the entanglements can't relax. So they're actually like a physical linkage of the system and becomes a rubber, basically, at that point, with a constant modulus that has to do with the density of the entanglements, right? And then if you get to the even higher frequency, so you're going to smaller sizes, then you reach a point where you're looking inside the reptation tube. So basically, it doesn't matter that they're entangled because at those size scales, the chain can just freely move. Like you're at a smaller size scale than the tube, so it can just go along its merry way, right? And at that point, it's a totally draining chain. So it's a Rouse chain. So it becomes like it's an oligomer. So I guess this is the frequency signature you get from the Rouse analysis. So two places you see it are in that plot of viscosity versus molecular weight, log, and the power 1 at the beginning for oligomers before you can have entanglements. Then you see this power 1. And the other place is when you get to very high frequency in a polymer melt, then you can see within the tube and the chains are moving following Rouse statistics at that point. So there's all these relaxation times for different events to happen. So this would be this is the time for Rouse transpose, like the Rouse relaxation time for the chains. And this is the kind of the viscoelastic relaxation time. And anyway, there's several relaxation times in this thing, but yeah.
Is the Rouse model and the repetition model, like with the gens, like the snake-like?
Yeah.
Is that the same? Is that?
Yeah. So the Rouse model and the reptation model relies on the Rouse model. So to say it's got Rouse behavior like within the tube. So you have the tube made up of entangled chains, and then within the tube, the thing can have has Rouse behavior. So that in order to calculate, let's see, I think it's in here somewhere. See, this is kind of a mess at the end here, but anyway, yeah, within the tube, it's Rouse transport, and then you include the kind of complexity of the tube. So you'd say the tube is a Gaussian pathway, and then you can get this higher, then you can get to the higher power for the viscosity, just somewhere at the beginning, right here. So then you get this, actually it predicts that it would have a power 3 with reptation. In order to get the 3.4, you have to allow the entanglements to relax, or you have to do something. You have to kick the model somehow. So basically, reptation would predict 3, Rouse predicts 1. So you have power 1, power 3, and the actual measurement is 3.4 for a melt. And that's because this reptation model isn't perfect. Right. So anyway, so that's kind of the part of it, right? See, someplace here I have the predictions of these guys listed. Not there. It's in the middle of this. Let me just go to that, because that's what you'll see too. There's a lot of extra stuff in here. Actually, it's in these other slides. Let me just go back. I think it's in these older slides. The first thing this says, like, Rouse model. This thing. You can see there's a lot to this, so it's not really, but I'm not sure how much of it is really of use to you, you know, that's the thing. So it's a little bit like sifting through it. There's a slide here that compares like reptation and Rouse. Tudor Rouse. That's dumbbell and Rouse. So I want to go through, right? So in the end, yeah, why don't I do this one? Oops, here. This isn't in. Let's see. What did I just do? That's that thing. Why did it do that? There. All right, so if you in the end, the Rouse model becomes just a dumbbell model, and the dumbbell model is pretty easy. So you have so the friction factor times the velocity is a force, right? Then the change in energy with respect to position is also a force. So that's like a spring force. Like if you take a spring and stretch it, the change in energy goes with, so if you integrate that, you get so the force is the spring constant times how much you stretch the spring for a linear spring, right? So you replace du dx by k spring x, and then the friction factor you've taken out of that. Then you get that expression, then you have dx over x, which gives you a log, and then you have time. So it'll be log of x is going to be time, so x is going to be exponential of time. And then you have to have something to get rid of units in the exponential, so that's the relaxation time for a dumbbell, subject to so if you have a dumbbell that's got a friction factor, so you have a bead, right, that's got a friction factor, so the bead diameter is going to be the coil, like NL squared, square root of NL squared for the bead diameter. Then the friction factor is going to be Stokes' law, 6 pi viscosity times the hydrodynamic radius, which is also the NL squared thing, right? So basically you can get an expression. I mean, if you're just talking about a dumbbell, then it's just relaxation times the friction factor by the spring constant being the constant when the two dumbbells stretch apart and bounce back and forth. So it's just a differential equation that gives you that relaxation time. So the answer of the Rouse model in the end is going to be the Rouse relaxation time is going to be the Rouse friction factor divided by the Rouse spring constant, and then this thing called a del, which is a phase shift parameter. So I'll show you kind of what del is after. Basically, if you have a guitar string, you pull it, you pluck it, it's got different harmonics in it, right? So basically, the del is the phase shift factor along the, if the guitar string was made up of beads, then each bead would be like shifting. If you had a sine wave for the vibration, it would be shifting a little bit up and down. So del is the phase position, 2 pi would be the ends, and then wherever the angle is within the thing. So however many, so you break up the guitar string in here, it's a fixed number of beads, so you can only break it into the bond length, like the Kuhn length segments, right? And then that's going to be the maximum number of modes you could have in the string. So there's a maximum number of modes in this case because it's got Kuhn lengths in it, don't vibrate. That's the idea. So you're talking about vibrations of a string. That was Rouse's thing, and that. So Rouse's, let's see, let me just add on here. So Rouse was a guy, 1953, right? So, and then Rouse's 53 paper is here. That's the paper where he developed Rouse dynamics. It was his PhD dissertation from the University of Illinois. And then afterwards, he moved to this Franklin Institute in Philadelphia, just something to do with Benjamin Franklin. And I don't think nowadays this place, I think, is a museum, but at the time in 53, it was like Bell Labs or something. It was a research lab, although not as high ranked as Bell Labs, but a pretty good place, right? So, but this was his work when he was a graduate student at University of Illinois, right? So, and then so if you look in this, all right. So the weird thing is that his entire approach is based on this Einstein heat capacity model from 1912. Okay, so basically, so in materials, like heat capacity is one of the main topics for like thermodynamics and materials. Okay, so and there's the Dulong-Petit model, which was the original proposition that the heat capacity of a crystalline metal be like 3 times R, the gas constant. And it's a fixed value. And it has to do with, and Einstein actually figured out in 1906 or something that had to do with the bond vibrations. In other words, if you have to take up bond vibrations. Then Einstein came up with a model based on quantum bond vibrations in a metal crystal that could predict the heat capacity. And in the Dulong-Petit, the 3R works great until you get to like low temperature. So absolute zero, basically. And then this Einstein model describes like why those vibrations change as you go to low temperature. Right. So, and it's based on these kind of vibration things, right? But it didn't work like perfectly. So Einstein's thing was a pretty good match until you, especially when you got to low temperature, and this ends up being it isn't this 1/t squared dependence, it's a t cubed dependence. It's like a totally different dependence at near absolute zero, right? So in 1912, Debye came along and like figured out like how to make that work. Okay, so the Einstein idea, so you break apart like if you so temperature is making the atoms vibrate, and it's as if there's springs, just like the Rouse thing. So you have springs and beads, and they're vibrating. So all the atoms in the crystal are vibrating. That's how it absorbs energy. So dq dt is the heat capacity. So that's how you get the heat capacity. So Einstein was basically, in his proposition, was that there was one frequency, like this Einstein frequency, and then you could describes so one frequency of vibration that describes the whole curve. And then in 1912, Debye came up with a model about how things actually vibrate. So the Debye model is this dashed line. And the Debye model, if you talk about density of states, so frequency is energy. So how is energy distributed in these vibrations in the material? Debye's got a spectrum of energy, and then he's got kind of a cutoff for the frequency. So he's got a function that describes that spectrum, and then he can figure out what the cutoff for that is, so the cutoff is just like the Rouse thing. There's a fixed number of atoms in the crystal. So that there is a maximum energy that you could put into it, because that's going to be the highest frequency for the vibrations. And that's going to be the separation between the atoms. That's called the Brillouin zone, basically, of the crystal. So Debye developed all that Brillouin zone concept and this vibration thing for metal crystals in 1912. So by the time Rouse got to grad school in 1950, this was 40 years old, right? So it's basically the textbook stuff. So stuff that was invented in 1980 to you is like what it was to Rouse when he got to University of Illinois and they're studying like heat capacity at some point, right? So then he's talking about, then they're looking at polymer viscosity and like how would you describe it? And Rouse took that idea of Debye's about this vibrational modes and just poured it into polymers, because in the end, Debye, instead of taking a 3D crystal in Debye's paper, instead of taking a 3D crystal, he says, well, X, Y, Z are the same in this crystal, so I'm just going to look at X. So Debye looks at a string of beads hooked together by springs that vibrate, which is exactly the same problem as a polymer. So Rouse took that idea and kind of just popped it and said, that's a polymer. Debye said, I can take that 1D and then I can do it 3 times to get the 3D, right? So because a 1D problem is simpler to solve. It's like, so Debye's thing was like this. So the first order mode, second, third, and then finally you got a fixed number because the atoms are at certain locations. And within one of those ranges of distance, that's a Brillouin zone for the crystal. And then you can calculate the heat capacity, and you can get that good match to it, like the dashed line. Right, so it works. On the other hand, it's more complicated and a little bit more complicated, and the Einstein thing works fine for most people because no one's at like 0 Kelvin. But so you only got to be worried about this in certain circumstances. What was like a coup for Debye? This is one of the main things that he did. This heat capacity. All right. The other thing is that he took because he could describe the vibrations. And if you look at a diffraction pattern and you see the atoms, like in aluminum especially, or like low density metals, the atoms vibrate a lot. They have a lot of motion. That's why it's low density, because it shakes out space and makes it a larger lattice spacing in it. So then the density is lower, but they also have this vibrational component that broadens the peaks to the diffraction. So you can measure this vibration directly with diffraction by measuring the breadth of the peak using what they call the Debye-Waller factor. And that gives you information about how atoms vibrate. In fact, from the Debye-Waller factor, you can calculate the heat capacity from diffraction. Like 2 things that have nothing to do with each other. Right? So we could predict the whole cycle of how things fit together and kind of what's going on in metal crystals, especially using that. So anyway, so this was sitting there in books. And you can see like, so the model is basically like you have a string of beads, which are atoms in crystal. This is the lattice spring constant for the crystal is a spring. And then you're right that you have like a spring N, and then if you pull spring N plus one, it's going to pull that one too. And if you pull the N minus one, it's going to pull it the other way. Then you have the spring constant, and you can calculate what the force is on that. And this is the same equation as for the dumbbell, but you have the velocity, the derivative, the force is the derivative of energy to that mass, except he's using mass times acceleration instead of friction factor times. So there's no friction factor in a crystal. There's no like drag coefficient to move in the atoms. So you don't have a friction factor, but you have the momentum part. So you have the mass times acceleration as the spring constant. Balance those two, and then you can get the Debye thing for heat capacity, which ends up being like a description of frequency and things. So anyway, and this is a picture of the Brillouin zone. Like in terms of, instead of talking in space, you talk about in wave vector k, which is 1 over, it's like q, basically it's q. So it's showing like this is the function that he gets for energy distribution as a function of position. And the Einstein just had one number for it, like just one vibration thing. So that's kind of, that was already existing. So Rouse took courses in this and studied this because this was like this was like a major discovery. I guess it could predict a lot of things about how metals behave, metal crystals behave. So anyway, I think it's important, and none of the books like mention this for some reason. One reason might be that if you go back to the if you go back to the 53, I think historically it's interesting to look at how things happen, but maybe it isn't to everybody. But so this is Rouse's paper where he gets the Rouse equation, the power one thing. If you go like find Debye in this thing, so there's one citation of Debye, but it isn't Debye's heat capacity paper. It's a paper Debye did on intrinsic viscosity for a non-draining fluid, like the Zim equation, right? So he's saying like Debye, the Zim equation, and then he's kind of saying like, oh, just off the top of my head, I got this idea of a bunch of beads hooked together with springs that vibrate, and it's going to be like a modes of vibration in it, right? So that you talk about the Rouse mode would be like the highest order mode in the polymer chain. From that, you get the Rouse relaxation time, which is the dominant relaxation time for the polymer. They can predict the relaxation time dependence, which ends up being n squared. And then the viscosity dependence, which ends up being times the molecular weight to the power one. So he gets all that from this kind of vibrational analysis. It's exactly the same, ported directly from the Debye heat capacity thing. But in the paper, he never cites Debye. So that's why no one put two and two together, because you've got a bunch of organic chemists, kind of looking for, or engineers that are looking for, and they've never heard of Debye, because they're just running extruders, right? So they don't have any idea that existed. Then you have a guy that probably took a course on it, got the book, and then so it's kind of a funny thing. Like he almost hid the fact that he directly copied the Debye heat capacity thing from 1912 in his 53 thing, and no one ever makes a connection. Like if you look in the books on Polymer Physics and you say like Rouse, no one mentions Debye about that. So it's really pretty weird. It's really pretty strange that no one even makes a connection today between the two. So I think it's really strange that especially because there's a lot of smart people and no one seems to get that. Anyway, so anyway, let's see. So I want to just go through the kind of go through the, let's see if I can hide this guy again. So that's them. Let me just go through in the context of that. So this is the same. You see the Rouse derivation is exactly the same thing. He's got, instead of calling it X, he calls it Z. So this is the distance along the chain for the different beads. And then instead of using mass times acceleration, he's using friction factor times velocity. So that's kind of the difference. So Debye gets that the frequency is going to be the spring constant divided by the mass, because he used mass times velocity here. And then Rouse is going to get, it's going to be the friction factor divided by the spring constant. Just because it's kind of a little bit, because there's no viscosity in a crystal, and he's ignoring momentum in this case. I mean, it would be a more complicated answer if you included momentum, but actually, because the polymer mass is so small, they make the argument that there's no momentum, you can ignore it. So you don't need mass times acceleration. So anyway, so instead of like in Debye's thing, it would be a harmonic oscillator, because if you have momentum, then the thing goes back and forth like a vibrating. And in this, it just relaxes, because you just have a drag coefficient and a spring constant. So it's just like a dashpot kind of thing, dashpot and spring thing. So it's just a damping. It's just a damping decay. I have that in here somewhere. Wait, well, anyway, so one's a harmonic oscillating, and the other one's a damping decay. But the math and the picture of the thing is a string of beads with springs is exactly the same thing. It's directly lifted, right? So, and you end up with kind of the same thing. You end up with modes of vibration, and you break the thing into the different modes. So the problem with this whole scheme, and also the problem, it was a problem also with Debye's model, is that if you have a polymer chain and it's n units long, and you're talking about this top equation, so you have the motion. Well, what do you do when you get to the beads at the end of the chain? Like, they don't have anything on them, right? So I would say, just have one spring and they're just hanging out there. And then that kind of multiplies, because then you could take the first three beads, then well, there's no tension on the end of it, right? So you can't exactly solve that problem. You need a closure for it. You need to say, what's the tension on the first bead? Because it's just dangling off the end of the chain, right? So it's different than all the other beads. So anyway, there's two solutions to that. I mean, you can say that that thing is just free and doesn't have tension, or you can say, I mean, two common solutions. The other way is you say the polymer is so long, you just a cyclic. So if you bond the last unit, so a cyclic would be the same as a linear chain. So the cyclic closures, and those two closures, every time people talk about polymer dynamics, they're going to have those same two closures that they use as the two prominent closures. It's a ring of huge molecular weight, so it doesn't matter. Or the end units are just hanging there doing nothing, right? Not contributing.
The end units are also, you can say that it's largely normal, like an atom normally vibrate, right?
Yeah. Yeah, but there's no, see, this is really coarse grain. So I didn't mention that. This is coarse grain. So that means that, so Rouse actually invented coarse graining in 53, because he said, so he has the chain. So he's going to have these units. They aren't Kuhn units. They're units that are larger than a Kuhn unit, so that they're large enough that they can follow Gaussian statistics. So that the size of his Rouse unit is going to follow R squared and L squared. So you can figure out what the size of it to get the friction factor from Stokes' law. And they're large enough that they have a spring coefficient that acts like a Hookean spring, so you can get the spring coefficient from the thing about taking the derivative of the energy thing that we did before. Like 1 over the molecular weight would be the spring coefficient. But they're small enough that you can divide the chain into these units, and there's a huge number of these units. And he doesn't say how large they are, but just that they will follow those laws. So that's kind of his thing. So the end unit isn't a molecule, it's actually like a polymer. So you can't exactly just say calculate the spring thing for that, like you could for ethylene or something like that. With the covalent bonds, you can figure out what the flexing modulus or stretching modulus is, right? But so yeah, it's a good idea, but that it kind of wouldn't work here. So you have to say you have to either say they're all the same, or that thing is just dead. Those are the two options, more or less. And then every kind of simulation of a polymer is going to be if you're doing the dynamics, you have to make that some kind of assumption like that. So anyway, so he did he did invent things like so how you actually fit this picture into a real polymer. So in Dubai, the polymer is just an idea, like there's a pathway through the crystal that's a linear chain of atoms. And then he just said, oh, that's a polymer. And then he also said the thing about momentum. It's not momentum, it's going to be a drag coefficient. I guess there was some invention going on in this, but it's really pretty close. The analysis is, so whenever you have this guitar string thing, the answer is going to be a wave. So he proposes this wave analysis of it, which is exponential I L, or I times the angle is going to be like a sine wave. That ends up being a sine function. It's like sine of the angle plus I times cosine of the angle. So there's an in phase and out of phase part to it. So this is a description of a sine wave, and then he's got this linear damping coefficient that looks a lot like the dumbbell thing. So the dumbbell ends up giving you a linear damped exponential decay. So this is you make a proposed solution to that, and then you can solve for tau by plugging that into this, and then you can solve for tau on that, and then you end up with tau is this expression. 1 over tau is that thing, which looks like basically tau is the relaxation time is going to go. These are the modes of vibration. So the relaxation time has a maximum relaxation time at the highest mode thing, which is exactly the same what Debye did. So Debye ends up with that spectrum of energies, and it cuts off at the highest one. So it's the same thing here, but he has a high-end cutoff, except here the high-end cutoff is defined by the molecular weight, and then in Debye's it's just a cutoff. Like he gets a Debye temperature for every material that has to do with the frequency. Like the frequency h nu is going to be the energy, which is kT. Then T would be the Debye temperature, and nu would be the Debye frequency for that high order thing. Anyway, it's pretty complicated, but it's pretty complicated. So it's a question of like how much of this do you actually need to know to operate in the Polymer physics spectrum? You need to know some of it. Like you need to kind of have a rough idea what's going on. The bead spring model, I think it's useful to say it's exactly the same as the Debye model for heat capacity, and it was just lifted with slight adjustments. And then the predictions of it, like what does it predict? So again, it's like cyclic boundary conditions give one answer. They're the same answer basically. They're off by factor of 2 in terms of the relaxation time, but basically the molecular weight dependence is the same. So you can do the cyclic boundary condition, or you can do the free end boundary condition, and then you get kind of the same answer. So anyway, so then he figured out like the highest order mode was important because he figured out the amplitude of the modes, the amplitude of the vibrations. And Debye did the same thing. Debye figured out the energy of the vibrations, figured out what the important one was. So in both cases, you end up with one mode that dominates the process. And then it's basically, when you work through it, the answer ends up being the same between a kind of a dumbbell model, which is just you have the velocity times the friction factor is a force, and then the spring constant times the position is a force. You equate those two, dx by x is log, so you end up with an exponential, and you end up with basically the same function, just if you just consider a dumbbell. So in terms of, so first off, if you just say that the polymer is a train and you add cars onto it and the viscosity goes up, that's one way to look at it. That's the Rouse model. You can look at it as really complicated Debye frequency thing for the heat capacity. You can get the same answer roughly with a lot more details in it. Or you can just say the polymer chain is a dumbbell. The whole polymer chain is a dumbbell when you pull it through the fluid, and you get the same answer that way too. Right, so it's kind of like there's at least three ways to look at this thing. People gravitate to different ones, so basically the simplest would be just you add a car onto it and viscosity goes up. So again, like there's some evidence for it at the high frequency end, you get this dependence that he predicts for this thing. and for the storage modulus. Those things you don't need to look at. This is the dumbbell. So this is a kind of, so we got a few minutes, but so why don't I just say a few things about this stuff? So you have like, this is the kind of picture that people are looking at. So you have a Brownian motion, you know, and you can find that on Wikipedia. They show like particles jumping around. There's somewhere, if you look at Brownian motion on Wikipedia, there's a video of particles moving around, and they show this kind of plot of the position. So it's like particle jumps because the temperature moves it, or because, so if it's a large particle and it's in a gas, the gas atoms hit it and make it move. And that's the original idea of Brown, like the dust, pollen dust particles that he was looking at in a microscope. And he's saying like the gas atoms hit it and then make these jumpy moves, right? So you have these jumpy moves are inherent to Brownian motion, and there's kind of a decay towards some average position of the thing, right? So this is like a spring. So the spring with some kind of being jolted, and then it goes back, and it's jolted again, and it goes back and back, right? So this, in terms of modeling this in a computer program or in simulation, see, those jolts are delta functions. In other words, they're instantaneous. So there's no time component to them. And so you have a thing called del t, which is a delta function, which is like a 1. So number 1 when it's at t, and everywhere else is kind of 0. So it's just a thing that's going along like boom, right? So this g of t is that boom. That's like the delta function. Yeah.
So thinking about kind of the train analogy, it's like the cars are relaxed initially, and when you pull on them, the inertia kind of prevents it from moving for a second, and then it pulls it along
Yeah.
slowly.
Yeah, that's true. But there's nothing, it's a train that's moving by Brownian motion. So it's not being pulled by an engine.
Yeah.
So it's kind of like moving randomly. So it could be one of the cars just gets lifted off or something, or so you could just jostle the cars in the middle too. But yeah, you're right. There's like a time lag. That's exactly what this del thing is, right? So you talk about, this is the time lag of the thing. Like in other words, the first car pulled and then it's taking like, that's kind of looking at the time lag of it. So it's basically the same thing. You end up with the same kind of picture of a train, just what you said. Like the first car moves, the last car hasn't moved. So there's a phase to it. You know, so there's like you're in phase at the beginning and you're way out of phase at the end. You know, so the whole thing has kind of a phase to it. It's also like vibrating like a guitar string. So it's like it's got all different modes of vibrations. That's just like the largest mode. That's the lowest order mode, what you're talking about, like just a one wave, actually half a sine wave for the whole train. So there's also like all these other vibrations going on. Anyway, it's kind of interesting, but you know, I mean, you don't need to get that deep into it, I don't think exactly, but anyway, but this stuff about the G is kind of useful because you'll see this if you look at computer simulations. They'll throw this function and you won't know what it is, and what it is that's just saying Brownian motion, because without input some motion into it, you don't get any response. So it'd just be like a dead equation without the G of t. So G of t lets that thing behave, so you can see how it behaves for kind of Brownian motion. And then so let's see, somewhere in here. Not really need that. I was going to organize these things again, but I didn't do it. I wanted to talk about a little bit about the relaxation time thing. Not in these slides. It's in probably over here. So that's dumbbell. Maybe I should just do a little of that. This thing. Okay, yeah, that's what I want. So this business about, so this is called linear response theory. So you have this, what's called a response function, which is the response to that delta function thing. So you have a delta function, boom, you pop it, then how does the system respond? So if you have a spring and it's kind of like a pendulum, so it would move and then it would decay with time and finally stop. Right, so that's called a harmonic oscillator. That's a damped harmonic oscillator. So this is what this response function looks like for a damped harmonic oscillator, like zoom, ding, 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 goes down to nothing. So that has both mass times acceleration and also a friction, like a drag coefficient, velocity times a drag, and the spring constant. It's got a spring, a dash pot, and it's got momentum to it too. So it's large enough objects that they have momentum. So you can't ignore the momentum, right? So the momentum allows it to be a pendulum. Like if it didn't have momentum, it wouldn't like go back and forth. It would just decay down like that part, right? So, and that's what you get if you have no momentum, so this is really Debye's heat capacity thing. And this is kind of what a polymer is, because polymer is so small that particles are so small, they don't have momentum. You can ignore the momentum part. So it's just a motion and then a decay, right? So these are different. So people talk about the response function. I mean, not many people, but some people might talk about a response function. So damped harmonic oscillator, then this is really polymers. It's going to be this exponential decay. And then if you have a fluid, so you kick a fluid and it moves and nothing else happens. So it's just instantaneously, you push it, it goes over there, and then that's it. You spill it on the floor, it's on the floor, that's it. And if it's a solid, you push it and if it's just a delta push, you push it and it comes right back. If it's a Hookean elastic, it's like boom, boom. So this is like the Hookean response function. This is a viscous response function, damped harmonic oscillator. So the reason to say this is that if you have the response function, then you can calculate any mechanical or viscous property of any material. So it's the universal. So mathematically, you can reduce measurements of the modulus, or measurements of the loss, or measurements of the viscosity, or the complex viscosity, which would be like a modulus. Any one of those measurements, creep compliance. So if you take the thing and put a weight on it and just watch it stretch out, or if you take a stress and pull it and then watch this tension drop with time, right? If you had goo and you pulled it. So originally it would have a high stress and a drop. Any of those measurements can be converted into this response function through integrals. And then basically, once you have the response function, you predict any other property of a material. So that's the linear response theory. Like there's one function that rules the world, and you can predict everything from it, every mechanical thing from it, right? So this idea didn't come from mechanics, though. It came from dielectrics, where you have so you can pulse things with an electric field and watch the polarization change. It's a dielectric kind of spectroscopy is where really, so these are all like signals, right? They're almost like radio wave signals. So basically, these are the responses of different things like capacitors and resistors and things, and inductors, right? So you can kind of see, so the original of all these things came from electrical engineers, basically. And then in Debye, I think Debye was an electrical engineer originally in training, but
This is all kind of resistance to change.
yeah, right. Right, it's a similar, and then you could do, yeah, so it goes to fluids too. So it's like fluids mechanics and electrical behavior are all linked together, but the parent of it all is electrical, surprisingly, because the other stuff was around for a much longer time, but you weren't forced to look at it in these terms before you had electricity. When you started having electricity and weird stuff like induction happened and it mattered, then all of a sudden you had to have a way to describe it. And the only pathway to do that was to go through things like response functions, right? So, but then once people figured that out, then they're starting to deal with polymer rheology, which is a complicated system. It's got loss and elastic in it. Then you realize like you can just adapt this stuff and pull it in. So there's a problem that this stuff, the nomenclature of it, like susceptibility and response function, all these terms come from electrical engineers or electric physicists or whatever you call it, right? So there's a problem in like looking at it and saying, how does that relate to a modulus, or how does that relate to a compliance? But so anyway, so I wanted to mention that.
Is there a way to I'm sorry, I'm just thinking, trying to relate it to what I've been learning in another class, but that response function.
Mhm.
So if you change the response function, you'll get different like properties, right?
Yeah,
And so,
I mean, it can be a liquid. In this case, it could be a liquid or solid or a viscoelastic, or it could have it what they call anelastic behavior. So there's like the three options for normal stuff. Goo, say goo, you know. I mean, if it's a crystal, you get hook in and that's it. You know, there's no other thing in it. And if it's a fluid, you just get that fluid response B. But when you get into things that are kind of part fluid, part viscous, and then they can be part something else. So like structuring and things like that, then you have to have like, you know, then you have to deal with it as a function. But anyway, so you don't need that. Yes, that's all. I think I just wanted to mention that because you can get a lot into this. If you wanted to see this stuff, you can go to like the Strobel book and it's on the webpage. Let me see if I can go back there. But that's got, so that he was originally a dielectric, so electrical guy, and then he went into polymers. And the book is written from that perspective in a sense. So he's got chapter after chapter about this kind of thing. And it's pretty well described. He's German, so it's a little bit not perfect, but it's pretty well described if you're interested in it, you know. So, it's good to read, I think, but basically it's hard to tell exactly where it's contributed to solving problems and things. Let me see what else I wanted to mention in here. Yeah, I just wanted to mention the few things and give you a feel for that stuff. Yeah, those are the predictions of the Rouse model. So the modulus would go t to the 1/2. So that we saw at the high end of the frequency spectrum. In other words, t to the minus 1/2 the frequency to the 1/2. So at the high end of the, when you really, so really actually if you're doing DWS measurement on a polymer solution, you get to the really high frequency part, you see that frequency to the 1/2 power. It's 2 and 1 at the low end, then it goes plateau, and then it goes to 1/2, going up at a lower slope, and that means that you have Rouse transport, and the thing that there's no reason to believe there is, except that there's a tube, and the thing's weaseling inside the tube. You know, so, and then the viscosity goes with power 1. That's kind of the important one. And the relaxation time goes with the power 2, like molecular weight to the power 2. So it's a stronger dependence of well, that's all there is in that thing. Anyway, that's about it, I guess, you know. And so thanks for showing up, 2 people. It's like everyone else online, well, disappointed. But anyway, so Friday, I'll have like 2 papers on Friday. So are you guys done then, or you're both undergrads, right? See, you're your 3rd year. Okay, but you don't, let's see, oh, you need to take the final. Okay, all right, good. All right, so yeah, Friday I'll go through the final, like dig up 2 things and put them together. It'll be like 2 papers. Hopefully it'll be okay. Yeah, all right.
Thank you.
Thanks.